Good day, everyone. We're now ready to start our webinar titled Luminescent Nanoparticles of Metal Oxides. Thank you very much for joining today. I'm your host, Mike Lasecki. Let me remind you that this webinar is hosted by ATE Central. They provide the Adobe Connect system that we're using. ATE Central is the information hub for the NSF ATE grantee community and provides all sorts of resources for teaching and technical content as well. atecentral.net. This webinar is brought to you by a collaboration between the National Nanotechnology Coordinated Infrastructure Southwest at Arizona State University and the NACK network at Penn State University. Thank you to our sponsors. It's me on the left, Mike Lasecki. Many of you have received communications from Janet Pinhorn. She's part of our group. Thank you, Janet. And Shannon provides IT support in the background. Thank you, Shannon. Also joining us today are two moderators. Uzgar Kekmak is Assistant Professor at Penn State University. He's a member of the NACK network. Thank you, Uzgar, for joining us today. And Trevor Thornton is Professor at Arizona State University and head of the NCI Southwest. Trevor, thank you very much for joining. Would you come along and come on, please, and say hello to everyone?
Thank you, Mike. Thanks for the introduction and for organizing this webinar today. I'm excited to hear Dr. Mao's presentation, so the audio sounds good.
Good. Thank you, Trevor. Uzgar, we've already checked in with you audio-wise, so I think we're all set to go. Colleagues, the webinar is being... Good. Thank you, Uzgar. The webinar is being recorded. I've turned on the recording button, and it's now my pleasure to introduce our presenter today. Wanbing Mao. Dr. Mao is Professor and Chair at the Department of Chemistry, Illinois Institute of Technology. Welcome, Dr. Mao. It's a pleasure to have you here today. I'm going to start to the next slide, and now I'm going to turn everything over to you. Go ahead.
Oh, hi. Thank you, Dr. Lasecki, and for the opportunity, and also, for the broad audience. I look at the list, it's from almost 5 continents. That's amazing, and I'll try to keep calm. At the same time, it's always the right challenge, for a professor to talk in front of some of their own students, right, and or group members. Because I used to talk to them, how to present, right? So, yeah, so in that way, I may be a little bit nervous, but I think the first thing is to acknowledge their contribution, right, to the research group. So here, I will start with, many of my previous group members, and so they did the work, and then here the image actually, the photo actually shows the group when I was still in Texas in last year. At the same time, because of all these contributions, from my students, and then I was awarded with the Council on Undergraduate Research mentoring award. So I appreciate that, and so. That's what I want to mention here. I really appreciate all my group members, and then also, I have a lot of collaborators, and here just list a few, across, so many places, and I appreciate their help, support, and also for financial, right? Nowadays without this financial support, then it's also difficult for us to do this research, and I've been fortunate to get all these awards, and then to do the work. So today, what I'm going to do is, I will give actually it's a quite long introduction. This is actually for a while I've been give an introduction that so many slides. I hope for those of you who have experience, in luminescence studies, then I hope I will try not to get you bored. And then I'm going to talk about some results, related to 3 types actually 4 types of luminescence, photoluminescence, radioluminescence, and persistent luminescence, and up-conversion luminescence, with a couple of type of materials. And then, I will try to summarize. So that's basically the outline about today's talk. First, I will start talking about, give a little bit introduction, metal oxides, that, important part for my research and my focus as well. And here, of course, we understand what the metal oxides, right? Definitely they have oxygen, right? At least one oxygen atom, and also at least one metallic element, right? In real situation, right? There are so many combinations because they can have, more than one metals. And also, as I will show you today, the metal oxides we've been focusing in recent years, they are at least have 2 metals. Because there's more, room to adjust the properties, right, and adjust the compositions. So that's one advantage of those type of metal oxides. And also, right, it's more challenging to synthesize them, right? So that's what we are working on. Here, I show 3 photos here, right? So first one showing here is actually several types of pigments. And then the photo here shows the phosphorus. And here is actually the ruby and the polished on the surface, you can tell, right? But the first thing I want to ask is, right, we talk about the pigments, dye, and phosphorus, right? What's the difference between them? Definitely, pigments are, they reflect light, they absorb light, right? But they don't luminescent. And the phosphorus, that's a different part, right? They luminescent. So there's a, even though, right, so good thing is they look colorful, right? That's what we like about. And then this ruby is also very useful, and not just as a gemstone, right? It actually the first laser was built based on the ruby, and it's called the ruby laser, and in the 1960s. So this is actually much more important than we think, scientifically as well. So that gives you a little bit, all these components actually are made of, many of them are made of metal oxides. So that's really, something I think, why I would like to focus on metal oxides. So then in terms of luminescence, right, what it is, right, is, it's definitely is light emission process, right? It's light emission. It is actually, an excess over the thermal radiation, right? We know that, right? Even our human body, right? We have a thermal radiation, right? So that's why the infrared detectors can detect us, right? Even when it is in dark. But for luminescence, that's different. It's actually the excess over the thermal radiation. That's also the first point I mentioned here, is a form of a cold body radiation. And then the other thing is, is different from the pigment, is because the light emission, it lasts for a time exceeding the period of electromagnetic oscillation, right? Because of this process. So it allows the correlation between phases of absorbed and the emitted light. So it is different from pigments. For pigments, right? For the reflected light or the stray light, their phases are the same before and after. But for luminescent materials, that's different. And I have a silly type here, so it's I have double O here. So please excuse me on that. And then, in terms of type of luminescence, right? There are all kinds of luminescence. You will probably heard about all these kind of luminescence, right? But what's the difference? I don't want to go through, each of them, explain, but I will focus on a few of them. for example, right? So the first one I will focus is for the luminescence, shortened the PL. And then for the luminescence, there are two types of processes. One is the fluorescence, and the other one is phosphorescence. I will explain to you what's the difference between them. And then the other type of luminescence is about the radioluminescence. And this is very useful for scintillations. So I will talk a little bit more about this in details. And then for the luminescence, there are other types of processes as well. As I mentioned at the beginning, up conversion and also persistent luminescence that can be, categorized under this. So that's this different type of. Before we go to the details, I want to give a brief history about this. The one thing I mentioned, related to persistent luminescence is actually there is another term. It's called afterglow, and this term actually showed in literature, in books, actually back to about 1,000 years ago, in some Chinese recordings. And then, more scientifically, it happened much later. For instance, the first observed fluorescence actually from Quilin by in 1845, and then Stokes actually coined the term fluorescence in 1853. Right? We will talk about what is the Stokes shift. For those of you who use the Raman spectroscopy, you know that, right? Stokes and Stokes. And then in 1888, then luminescence, actually this term was first used. And then so those are in the 19th centuries, right? But most of the basic principles of fluorescence was developed in the there is another type of, sorry about this, 1920s to 1930s. There are a few terms which I will talk more about this, excited state lifetime, quantum yield, polarization of fluorescence, and Jablonski diagram. For the powders, metal oxide, luminescent materials we're working on, we don't talk about the polarization that much, but for organic dye molecules, that's what a lot of scientists working on this. And then in the 1950s, right, the fluorescence resonance energy transfer was developed by Foster. So it is also called Foster resonance energy transfer. For those of you who work with bioimaging, this is a very common process. And then in the 60s, right, up conversion was actually developed by Oziel in the 1960s. So that's a little bit of brief history. I hope give you a little bit background on that. And then this is the one thing I was started talking about, then the Jablonski diagram. And you can see here, right, when we shine light on the material, right, so it will absorb light. So this is the ground state, and then these two are some of the excited states, right? So they will absorb light, and then there will be a vibration, relaxation process, and also the internal conversion processes as well. So then once it's on this state, and then it can be fluorescence. So that's the fluorescence process, right? But at the same time is for some compounds which especially have heavy metals, right? So it could, because of the orbital and spin coupling, and then it could have this intersystem crossing. And then once it over here, over this excited state, then it can be give out the fluorescence. And so that's the difference between the fluorescence and the phosphorescence, right? So mostly you will see when people are talking about the organic dye molecules, right, it's talking about the fluorescence, right? But for us, when we talk about the rare earth, talking about transition metal, elements doped luminescent materials, we mostly talk about the phosphorescence. even though nowadays, you know, we combine these terms, we just call them the luminescence. So that's also a little bit different. At the same time, is I really want to point out something is these time scales for all these different transitions. And because this is something normally, you know, we don't pay attention, but it's so important in terms of all these transition processes. You will see this absorption process is actually pretty fast, is in femtosecond scale. And then for the vibrational relaxation and the internal commotion is a picosecond scale, and fluorescence is in nanosecond, and then fluorescence is in microsecond, you know, or even millisecond scale. So that's why, you know, how this process was happening, and because of the different time scale. So that's one part of this. And then, you know, at the same time is, you know, to show that process, you know, a lot of times, especially for organic dye-molecules, you know, people use this type of diagram. It's called configurational coordinate diagram. In short term, it's called CCD, but it's not the CCD normally we refer to. And you will see that this shows the process, you know, absorption process, and then emission process, you know, either the fluorescence or phosphorescence process. And we also see this there is the inter-system cross-link process, right? So one thing we all mention is, you know, the multiplicity changed, right? So that's why this process normally is this process is normally a slow process. And also, right, you know, based on this CCD diagram, right, then we have this the energy difference, right? So this is absorption spectrum, this is the emission spectrum, right? So the big difference, that is the Stokes shift. And that's what I mentioned to you earlier. What is the Stokes shift about? And so that is a little bit about the luminescence. And then I want to get back to this process, right? You know, the ruby, and also how it's related to laser, right? So the laser, right? The first laser is actually, you know, the wavelength is exactly respond to this emission, the red emission is a red laser. And the question is how, right, to study all these processes. So that is a few techniques, you know, for people who work with luminescence, you know, we normally use, other than the other techniques, right? So the first one is excitation spectroscopy, and then so basically this process, right? You know, over here, and then emission spectroscopy is the process over here, right? Then the quantum yield, right? That means, you know, what's the difference, you know, between the emission and the absorption, right? The quantum yield, and then the lifetime, right? We talked about the time scale a little bit earlier, right? So how do we see this transition that happens? So these are the four techniques we widely used, and then some of the data I will show are based on these characterization techniques. So that's for luminescence, and then what I will do next is, you know, I will try to explain to you for each of this, and also pay attention one thing before I move to the next slide. The excitation spectrum is different from the absorption spectrum, right? For a lot of us, we are very familiar with the absorption spectrum over here. One thing to remember is when we talk about the absorption spectrum, when we take absorption measurements, right? This is the intensity of the excitation light, right? Difference, the ratio, I mean, after and before. And while when we take excitation spectrum, is actually is a different process, even though they are related, right? Because for absorption process to happen, you know, we need to excite our samples, right? But for also, right, for to take excitation spectrum, we need to have the absorption process happens. So, so I will refer to this next one to talk about the excitation spectrum. So you will see here, right? So this is the light source, and then the sample is here, And then this is the excitation monochromatometer. And then this is the emission monochromatometer. And then this is the detector here. So when we take the excitation spectrum, we fix the emission wavelengths. And while we are changing the excitation wavelengths, and so then we measure, at that specific emission wavelengths and how the light being absorbed by our samples, right? So this is also, you see this configuration is in the 90 degrees between the excitation monochromatometer and the emission monochromatometer, right? It's very useful for especially for the powder samples, where we normally work with, because they are not transparent, right? So we use reflect light to do this measurement. And then for emission spectrum, then is the opposite, and you will see here. So now the emission monochromatometer is actually the moving part. So we use a gradient to change the wavelengths of the emission. And then for the excitation is fixed. So then we use a detector to detect get the emission spectrum. So just as I mentioned earlier, I really want to show you, what the difference between the absorption spectrum and also the excitation spectrum. So I used this molecule as examples, and you will see that, right? So the absorption spectrum and excitation spectrum, the peak positions are the same because the energy levels, right? They don't change, right? But the difference you will see is the intensity changed, right? Because some energy levels, right? The absorption will happen, right? But that doesn't mean that is the best excitation wavelength. So that's what we see here, right? So this is a very good example. And also we will see, right, the Stokes shift between the excitation spectrum and the emission spectrum. So that's what I want to mention here. And then the next one I want to talk about is the quantum yield, right? A lot of times, right, for non-physicists, okay, when we see quantum, we will freeze, right? So I want to use this cartoon to show that, it's actually not, when we talk about the quantum yield, it's not really that that's a challenge, okay? So don't be scared with that, right? So what it is actually, especially for powders, right? So when we measure the quantum yield, we use this integrated sphere, and so the light get in, and then get on the sample, and without the sample, the light will reflect it. So this integrated sphere is actually internally is coated with a very reflective material. So there's very little energy loss. And then on somewhere else we have a opening, and then we get the light out. And so with that, then, what we can do is we can measure a few things, right? By definition, because by definition, quantum yield is the immediate photons, right? That is over the number of absorbed photons, right? How do we get that is, this is the measurement we do. So basically, we have the, so in this sample holder, we either leave it empty or we have a reference sample, right? And then, we measure the excitation spectrum, emission spectrum over, this emission range. And then we put the sample in, and of course, the sample will absorb the some of the excitation light. And so there's a difference, right, between without the sample or with the sample, right? And then, of course, with the sample, we will see emission peak here. And then we have this formula, right? So PB minus PA over LA minus LB, and that's how we get the quantum yield, right? So in that way, right, quantum yield is not that complicated. So we are not really talking about quantum physics, right? So then the other thing important is luminescence. So luminescent lifetime. So as I mentioned to you earlier, this process is actually quite a complicated process because there are so many steps. So in overall, right, there is the energy transfer process. There's internal crossover, all that processes, right? So add that together, but when we give this a pulse and then, of the sample, and then it will be excited, right? Then the luminescence will decay. And when that intensity becomes this ratio, right, then that is what we call the lifetime, the luminescence lifetime. And so the measurement is actually done this process. Right? So basically, this pod controls the pulse, and then we measure the emission over here, and then we get a curve like that. But one thing I want to mention here is, from sometimes when we get this lifetime measurements, they can be more than 2 lifetimes because earlier here I mentioned that there are so many components, right? So that is also happens because of the different decay processes. And also, by the way, right, when we talk about the lifetime, is when when the samples are in the excited state, instead of at the ground state. So that's the first part. Then the luminescence, what we are mostly focusing on is actually we have a activator, which we a lot of times we say the dopant in a solid state sample, which is we call it a host, right? And then we excited, part of light will be absorbed, then emission, and that's the main component of the phosphorus. And so during that process, right, then this is actually what I showed you, the diagram, very similar, right? So NR is a non-radiative process. And then, during that process, right, then it's more complicated, right? So it depends on where the dopant energy levels and also related to the host, right, where the valence band and the conduction band is basically the band gap where they are. And also, sometimes, the host depends on the excitation wavelengths. We can excite the host as well. So this could show the host absorption, and also depends on whether there are other components, in the samples, right? Sometimes we can use those as the sensitizers, and then the sensitizers transfer the energy to our activators, then it emit light. Of course, they can emit light as well. So how to adjust all these processes, that's the way how we tune the luminescence. So I don't want to spend too much time. I think I've been going too slow. Then what is a good host material, right? So but back to the CCD is, there are some discussions, if the host material is actually more structurally rigid, right? Then, you will see this, the minimum here, they get more and more close, they are even overlap. Then that's the ideal, host. So the objectives, what we want to do is to reach in, to get, search new host materials, and then develop nanometers, and how do we enhance luminescence, right? More importantly, fundamentally, we want to understand the structure-related mechanisms. So that's all the few things, I want to emphasize. But the first thing is, right, why we are focusing on nanomaterials, right? So in general, right, they have a high quantum efficiency and the sharp, emission peaks, high photostability, the emission wavelengths, actually we can tune that, and they emit light, when radiated by even ionized radiations. And so, and also, right, for some applications, right, we have to get nanoparticles, the bulk, some luminescent materials doesn't work, right? For one example I want to mention here is for bioimaging, right? So a lot of times, of course, people use the organic dyes, right? But they suffer from photo bleaching and broad emission. And then the bottom dots, a lot of them, they are quite toxic. But then for the nanocyanide doped or for transition metal doped nanoparticles, then they don't have those issues. So that's why, one of the motivations that we want to focus on luminescent nanoparticles. And so I will skip this, and I think I spent too much time on this part. Anyway, so any questions on this part so far?
Dr. Mao, thank you for that background. I appreciate several people in the chat window that have clarified this up conversion process. As I understand it,
yeah.
An up conversion process, you could shine near infrared light on a sample and have visible light or near ultraviolet light come out. Is that correct?
Yeah. Yeah, I will get back to that more, mechanism on that point.
Okay. Uskar,
Yeah.
is there any comments at this point before we go ahead?
Not from me, Mike. It was, a great, actually a summary of the overall quantum yield up conversion.
Dr. Thornton, any comments from you at this point?
No, that was a very nice introduction. Thank you, Dr. Mao.
Good. Go ahead, Yuanbing. We're happy at this point. Thank you.
Okay. Thanks. Yeah, I've been looking at the comments as well. Okay. So thanks for that. And then I'm start going to talk about some of the luminescent processes. So first I will go to the luminescence and the luminescence. And the first thing I want to mention is we use this type of compound as a host, which is called a 2M2O7, and A is a trivalent, and the M is a tetravalent. Of course, in this composition, it can have other compositions, but this is what we focused on. So one important thing about this type of compounds, they are well known have this two type of structures. Basically, they are the cubic structures. Other than that, because of this composition, and so there is called the disordered fluoride structure, and then the other one is called the ordered pyrochlore structure. The composition is exactly the same, but the difference we want to see is there is oxygen vacancy, and where the oxygen vacancy is located. And for the disordered fluoride structure, the oxygen vacancy is actually, it can be any oppositions of this these cubes here, showing here. But then for the ordered pyrochlore structure, the oxygen vacancy is actually is located in one of these cubes, while the other one, the metal, the A metal is actually coordinated with 8 oxygen ions. So then, of course, right, this we can consider, each of these cubes as a unit, right? But then for the pyrochlore structure, then we have this. We need to consider a larger unit cell. So that's why we have, for pyrochlore, we have the superstructure that terminology. So with that, then. In literature, right, then there's actually very important formula here, depends on the ratio of the A cation and the M cation. It has this magic number 1.46. If it's smaller than that, then it's a fluoride structure. Then if it's larger, then it's a pyrochlore structure, right? So that's one thing, very established in literature. And then the other thing about this type of compounds, this disordered structure and ordered structure actually could happen at a certain temperature. And so one thing, so because of this structure, right, by X-ray diffraction, we actually, it's very difficult to differentiate these two structures, right? Because X-ray one is more on the long-range order determination. So one technique we use to differentiate these two structures is use Raman spectroscopy, right? Because of this random oxygen vacancy locations. So invisibly, so for this structure we will only get one Raman peak, but this, by quantum calculations we get 6 Raman peaks. So that's one thing. You will show that. I will show some data there. The other thing I want to mention is, for this type of compositions, they have very high melting point, right? So in that is, in literature, when people make bulk samples, right, the synthesis temperature is always high, right? So, when the synthesis temperature is too high, it's very difficult to make nanomaterials. So that's why, how do we synthesize the nanomaterials? That's one thing we want to think about, right? But we also, right, because of this phase transition temperature, we also want to think about, design a synthesis technique which has a lower temperature, lower than this phase transition temperature. Then we probably can get the metal stable phase from our synthesis. So that's motivate us to develop a synthesis technique. This is actually a process, I developed when I was a postdoc at UCLA, and it works well, right? My advisor just asked me, to focus on type of hafnium based compound, because at that time, she's really into that type of compound. And then at the same time, as I mentioned to you earlier, I don't want to just focus on hafnium oxide, so I've been looking into this, and then, I started working on this type of compositions, A2M and 207. But at the same time, right, because they are complicated. This is not that type of perovskite structure, so it's more challenging to synthesis. And so I've been thinking about how to make that happen, right? The first thing is, when I was a graduate student, right, I started to, spend a lot of time to work on this type of process. It's called the molten salt synthesis, but then for this type of compounds, if I mix the precursors, like the A oxide and M oxide, just like that, by using molten salt synthesis, I cannot get pure samples of this A2M and 207. So I've been thinking about, how to we get A and M together before I use the molten salt synthesis. So that's why in this process, I have a first step here. So I use the co-precipitation process, right? So I use this nitrate or oxychloride, and then precipitate them by ammonia, and then I get this precursor, hydroxide precursor, and they supposedly, all the metals, they're supposed to mix well at the atomic scale, right? And then, I dry them, get a precursor, and then I can mix with the salts, and then calculate them, and then get the nanoparticles. And it worked, right? And also you will see this temperature is actually only 650. And compared with, the solid state synthesis temperature, this is very low temperature, right? Not talking compared with organic chemists, right? The synthesis. So there are many advantages of this process, right? Lower temperature, and also when we talk about the luminescence, right? The dopants, how evenly they distributed in the host materials, that's also very important, because we really don't want to form clusters of the host, the activators. Once that happens, right, the activators, when they form clusters, then they will have the concentration quench much earlier than it's supposed to be. So that's why, this is very important. And then the other thing is, by using this molten salt synthesis compared with the soil gel method, the nanoparticles we make, there's very little, aggregation, but soil gel synthesis, they aggregate. Even though, technically we can say they are nanoparticles, but they are aggregate, form much larger particles, mostly in micrometer scale. And then the other thing about this is, flux method, they also use salt to help the formation of the product during that process. But the flux method, mostly used to synthesize single crystals or crystals in the much larger sizes. And then the other thing is, to make this type of nanoparticles, we don't need to use any milling, and the milling process is actually very detrimental to phosphorus, because it forms some kind of amorphous layer on the particle surface, and which is not good for luminescence process. So that's the synthesis process, and we made that the type of nanoparticles. And then here, but I want to switch gear to talk about the luminescence, spectroscopy. And one thing we start to think about is, when we change the composition, how that will influence the luminescent property, right? So here you see, these are the undoped samples, right? The nanoparticles, and then we excited them at 306 nanometers, and then you see the emission spectrum is actually quite different, right? For the non-silicon zirconate, and we get one peak here and another peak here. But for the non-silicon hafnium, we get a single peak here, right? Of course, this is in this range only, right? We may get the other peaks, if it's a much broader range. So we just wondering, right? These materials, they are so similar, right? So on the periodical table, right? Hafnium is right below zirconium, right? What's the difference there, right? So we, collaborate with scientists, to calculate this, the structure and the energy diagram. And then we see that for non-silicon zirconate, and we see there are two peaks here, right? And this is related to that violet blue emission peak around 392 nanometer. And then there's another one related to the red emission at 707 nanometer. And of course, this is what the oxygen vacancies comes into, right? Because these are the actually undoped samples. And then for the non-silicon hafnium, and then this is the peak which is responding. But of course, there could be another peak, and but then, with our instrument we had at that time, we couldn't detect this peak. So with my new instrument, it's coming actually this month, and hopefully in the future we can detect this peak. And also, I want to get your attention is you see for these two compounds, their band structure is actually different, right? So if here you see the band edge is about 5, but here, it's 5.5, something like that. So that, definitely also makes a difference. So the composition definitely, will affect the many of the physical properties. And then, right, based on what I just showed you earlier, so now here, then later on, we actually, we doped these two materials with European at different doping levels. And so European here is, European 3+ is widely used, for luminescence purposes, and use the probe dopant. So one thing I want to show you here is, so this is the quantum yield, right? This is European doping concentrations. What we will see is that with these two host materials, so when it is non-silicon hafnium, they were at the same European concentration, the quantum yield is always higher than the other one, the non-silicon hafnium, right? So that's quite amazing. And then, if we really look into the chemistry a little bit, right, in this structure, supposedly, if European doped to the non-silicon side, so the coordination number will be 6. And also, when we look at the ionic radius, right, the coordinate is actually a little bit larger than the hafnium, right? Even though, hafnium has 32 more electrons, right? So that is how this happened, right? This is also so definitely we believe that extra electrons from the hafnium will affect the crystal field splitting of the European 3+ ions, and also change the charge cloud of the European 3+ ions. So That's why we see this different quantum yield. And so with that, then, I want to move to the next one, right? Earlier I mentioned about the photoluminescence, right? When we talk about the photoluminescence, the excitation wavelength, excitation light, mostly is visible light or UV light, right? But then, there are much more powerful excitation sources, right? So especially, with megawatt and gigawatt EV. And so, for example, when we use X-ray or gamma ray to excite our materials, and then that gives us the radioluminescence. And so the absorption process of the energy, right, is much more complicated. So I will not go into the details about this whole process, but this is a very important type of materials related to radioluminescence. And then, of course, right, when we want to detect the radioluminescence, it also, happens in the visible range. So that is what this figure tries to show you here. And then, so why this type of radioluminescence studies is so important, right? Just, mention a couple of things here, right? When we go to hospital, we have the CT scan, we know that is actually, to get a good CT scan, we have to this type of materials. It's called scintillators, right? And also right now, when we go to airport, even go to many, federal, for example, federal buildings, right? There's a security check, a lot of times use the scintillators. But then the problem with the current situation about scintillators is actually the progress on good scintillator development is very slow because it's very difficult, right? For mostly, people use single crystal scintillators. And for those of you who work with the single crystals growth, you will know it's actually pretty difficult to make a perfect, very good crystal at that size, right? So there's one way is, can we, develop other, can we have other ways to develop good scintillators, right? One way we can do is, right, we can use make a nano scintillator materials and then get them into the ceramics, right? So that process will be much easier, and also the doping process, will be much more uniform, right? So that's the one thing, I've been thinking about it in the past years, and also, right, there are other techniques, for especially related to bio applications, right? So that we have to use the nanomaterials, right? So that's why, it's very important to develop good scintillator materials at the nanoscale. So here, what I want to show you is, we start with this composition, so gadolinium, hafnium, doped with 5% European 3+. So again, we use the European as the optical probe here. One important thing is I want to mention here is, when we, with the modern salt synthesis process we developed, we synthesize this type of nanoparticles at 650 degrees Celsius, so it has a disordered fluoride structure. That's one thing I mentioned to you, right? We can synthesize this type of metal stable phase, at this temperature. And then what we did is actually we needle this type of samples, which is nanoparticles, 7 nanometers, the synthesized ones. And then, for example, here, with the 2 temperatures, then these nanoparticles, they will grow to larger particle sizes. And also, right, the phase is changed to auto the pyrochlore structure, right? So that is, nobody have been doing this because of our unique technique, synthesis technique as well. We can change the particle size of this type of combinations. But at the same time, more importantly, I want to show you here is, when we excite these 2 materials by X-ray, by the same X-ray, right? We will see that we get radio emission for this disordered fluoride structure, but for this larger all of the pyrochlore nanoparticles we get orange emission. So this is quite amazing, right? So to help us to design advanced optoelectronic materials, right? Especially the scintillator materials. And so that is one example. And then the other thing is I talked so much about the advantages of nanoparticles, right? So nothing is perfect, right? They must have some drawbacks for the nanomaterials, right? One important thing we know that is, the surface defect, right? Because it has a larger surface area, but at the same time, if it opens or at the surface, right? So it gives more chance to decrease the luminescence efficiency. So one way to overcome that strategy, overcome that problem is, to coat this type of materials. And so that's what we are trying to do, with this Coreshell structure. And at the same time is, for those of you who are very good with electronic structures and, with good physics background, you will see that, right? When we talk about the band structure, right? And now we are talking about here, because of the Coreshell structure, we're talking about the two materials, right? So if we can, for the shell, if we can find a material with the band structure cross over the band structure of the core material, which is doped, right? But the shell material is not doped. And then, we can have the photons, or the electrons from the shell material transferred, and the holes as well, transferred to the core material, right? And then that energy will help increase the luminescence from the core material, right? So this is like, one stone and the two birds strategy, right? So in that way. And so what we did is, of course, the synthesis is what I don't want to talk about it, it's not that straightforward, okay? But we eventually we developed a strategy, and we will be able to make this Coreshell structure, especially, this is not quantum dots, these are the metal, these are the compositions are showing here. So these are the complex metal oxide Coreshell nanoparticles. So the synthesis part is much more difficult, but today I don't want to focus on the synthesis part. But the important thing we will show you is, in terms of the photoluminescence, you will see that, with a different molar ratio of the shell to core, and you will see, when the ratio is about 1:1, we can increase the quantum yield, double it. We can double that, right? And also when we look at the radioluminescence, and we will see that, this ratio is a little bit higher. It go about like 2. But in terms of integrated intensity, is also doubled, right? Also, one thing I want to point it out to all of you is, here when we talk about the PL, we talk about the quantum yield. Here we only talk about the integrated intensity, because that's a measurement challenge. And for PL, we don't have the setup to measure the quantum yield yet, and also so how to get a specific wavelength so we can get a quantum yield. That is also something we don't know yet. But that's but definitely the result here shows the point, right? The Coreshell strategy is actually helpful to increase the luminescence. So that's one thing. And then
Dr. Mao, may I interrupt for just a minute? It's Mike. The fascinating Coreshell strategy. I'm just worried about time a little bit. We have about 15 minutes left, so I just wanted to remind you.
Okay, thank you.
But thank you.
So, okay. So then the other thing I want to mention is, I think this is a very good, area everybody are familiar with, because now a lot of times we use the LED, the light emitting diodes, lighting, the bulbs are more common, right? But then the thing is really, we're losing, the red light component is actually not that sufficient yet. So this is one thing we want to work on with something is, can we get the warm white light? So that is what this project is about. So what we did is actually, still based on this type of composition, but we triply doped them to get this type of phosphorus. And it has got many advantages, because now all the dopants are actually in the one host. Instead of we have, these different components, and we make this the powders of each of the singly doped, and then mix them, right? So this triply doped, so the energy transfer between the dopants also even can happen. So that is what we see here. And then you see, when we adjust the ratio of this, the doping level of these three elements, and then you see that, the emission from correspond to these three dopants actually changes. So one thing is, the emission from these two dopants actually, it can also excite the European 3 process well, other than the excitation source we use, right? So that's why, with that composition, we get warm white light here emission, as we're showing in this diagram. So for that part, then the other thing I want to mention is related to luminescence thermometry, right? Why this is important, right? If we have a moving part, we want to measure the temperature, right? That's not an easy task, right? But if we use luminescence, then it's possible. And also, right, in the other systems, right, if it's very small, right, just in like our body, right, when we go to see doctors, we get some thermometer, right, just measure measure our body temperature, right, at one point, right? But a lot of times, right, when we are ill, the temperature is actually, maybe caused by certain areas, right? And how to get to that, so this is, the nano and luminescent nanoparticles could play a big role, right? With the small areas. So, I'm mentioning a few advantages and the needs for this type of luminescent nanoparticles some metric materials, right? The important one is actually, how do we measure? One thing I really want to mention is how do we measure the temperature of the reduced areas? And so that is what this comes in. And but the current, thermometry materials may not work that well, so that's why we want to work with nanomaterials. So here you will see that we use this composition, and though what it is, right? How this works is actually, when we have different temperature, exposed our materials to different temperature, and then the luminescence actually the intensity will change, right? So in general, this will decrease, right? Because of the thermal quench. So this is exactly what we observed, and then based on this curve, we can measure calculate the sensitivity, and so this is what we got, from our samples. Compare our samples to what's published in literature, and then you will see, in this quite a wide range temperature, and actually our sensitivity is pretty high. It's because many advantages of this structure and the composition as well. And of course, for thermometry, and there are other type of techniques to measure this this change with the temperature, right? For example, the lifetime, that's one technique people widely use. And also there is a ratiometric process as well. That means, if there are two, for example, there are two emission peaks, one peak doesn't change with temperature, and then the other one change, the other peak change, and then the peak doesn't change, that's set as an internal standard. So those are other techniques have been used. And and then the other thing related to this is the nuclear waste mobilization. And we know that, right? Nuclear energy is a clean energy. It doesn't cause too much problems, right, environmentally. But at the same time, the waste, that is the problem, right? So how do we stabilize that? So considering the A2M207 structure, so we thought about, it has a very good structure. So can we use that for this purpose, right? So here we look at the three suitable properties. large containing capability. So we want to dope those nuclear waste materials as much as possible, right? Whether the material has high thermal stability and how radiation stable, right? Because in this nuclear waste, there are a lot of irradiations, right? Ionic irradiations. So that's what we've been working on this. And we showed here, we really can dope to high level. And this is 0%, and then this is 15%. Actually, we have demonstrated actually, in our lab, you can go to 35%. Uranium doping as well. And so, and then, the result I'm showing in the next two slides is not related to luminescence, but I thought this is a good topic to show, but at the same time is, we can, related to luminescence is related to speciation of the uranium ions, because different uranium ions and they show different emission peaks. So that's not talking today, but this is something related to the. So here I talked about this point, right? I'm going to the next point, about they show the high thermal stability of these materials. So here we showed that when we heat this sample up, we see the structure change, right? Again, this is Raman spectrum that I told you earlier. And then the other point is, when we cool it down, the amazing part is, the structure change back, right? So that's very amazing. So that it showed that, this phase transition is actually reversible. And that's very important, right? Because, when we use this material, the nuclear waste containers, right? This, the temperature variation, is not just one cycle, it can happen many cycles, right? Of course, in terms of the experiment, so we wish that, we can test our materials with more cycles, but that's one thing, next thing we want to do. And then the radiation stability. So we irradiate our samples with gamma ray as well. The important thing with these two compositions, these are the two extremes, right? AOA, the lanthanum is actually has lanthanum 3 plus is F0, lutetium 3 plus is F14, and then because of that difference, and then we see that they show quite different changes with the when we irradiate our samples with gamma ray with different doses, but eventually they get back to the original structure. So that's very, very interesting observation. So to summarize for this part, right? So I talked about the synthesis, by this modern salt synthesis process. In terms of the spectral tuning, I mentioned, I showed a couple of examples, by this actually, I mentioned this these 6 strategies here, and I showed you some examples. In terms of the applications, I showed you 3 examples as well. So for that, I know I've been slow, but if you have any questions, and before I move to the next point.
Dr. Mao, it's Mike. Thank you. I just want to mention on time,
yep.
Colleagues, we're right at the top of the hour now, and Dr. Mao, we'll probably limit you to another 10 minutes or so. Colleagues, if you are out of time for this webinar today, of course, you may have to leave. The recording will be available. Dr. Mao, I'm guessing we may not be able to get to upconversion, but the persistent luminescence will probably work. But I would there's a couple of questions. I'm going to turn to Trevor Thornton and have him forward one of the questions or 2 of the questions to you. Trevor, go ahead.
Thank you, Mike, and thank you, Dr. Mao. Fascinating talk. I noticed we had more than 60 attendees at one time, so that's terrific. A few of them had questions about the size of the nanoparticles, and I think you addressed that in some of the earlier slides. You showed how I think the nanoparticle size changed from, what was it, 7 nanometers to maybe a few hundred nanometers when you increase the temperature from 1,000 degrees to 1,300 maybe. But there was a question about lower temperatures with the calcination process. And in particular, one question, will the high temperature, the long calcination process result in overgrowth of nanoparticles at temperatures of around 600 to 700 degrees? What do you think? Is that an issue?
Definitely. So the nanocrystals will grow, depends on the calcination temperature and the duration.
Yes. Okay. So good. Thank you for asking that question. And maybe for time's sake, we should.
Okay, thank you. But there are techniques to. I actually there's recently there's a science paper. Somebody developed a technique to heat up the materials very quick in like 20 seconds, 30 seconds, up to 2,000 degrees Celsius. I've been thinking about maybe we can apply that to our nanomaterials. But anyway, I'll move on to the next one. So in terms of persistent luminescence, what's the difference with regular photoluminescent materials? Once they've been excited, they can luminescent for minutes, hours, or even days. Even we remove the excitation source. So the mechanism is quite different. So for persistent luminescence, based on the current understanding is because they are traps, electron traps or the hole traps, right? So they store the energy, and so when the irradiation source removed, then those traps, those electrons at the traps, they will get back to the band structure or directly transferred to the activator centers. And that process is only with our the thermal vibration, that's enough. So that's what the persistent luminescence it works. And then there are many kinds of applications, because of the time. Then I won't go into the details, but you can imagine, there are many kinds of applications. So I will focus on the results. So the materials we are focusing on is actually, with this type of compositions. So the zinc galate, it has a spinel structure, and we use the chromium as a dopant because it emits at this specific wavelength, which is in the near IR range. So that is very good for the biological tissues of the optical window. So that's why we work with this. But in literature, there are many studies on this, but the syntheses are not perfect. So that's what we want to move on, and we use this biphasic synthesis. So the nucleation process starts in this water, the aqueous phase, and then the growth process starts, happening in this organic phase. So that's help us to control the nanoparticle size and as well as their size distribution. So that's what we got, for example, this sub 10 nanometer nanoparticles. And so here, then we look at their excitation spectrum and then the emission spectrum here, and you will see that, each of these peaks actually we can assign them to specific transitions. Importantly, these two peaks actually like the DD transitions of chromium 3+, and so this is the emission process. More importantly, it showed the persistent luminescence process. So we excited the materials by 254 nanometer UV light, and for 5 minutes, then remove it, and then we see that the luminescence actually will keep happening, for more than 1 hour. When there's no nanoparticles, of course there's the background, but our nanoparticles show the luminescence. So then the question related to this is, it's a very good synthesis technique, but the amount of samples we can synthesize is really, really small because how much precursors we can charge into this solvents is limited. So we get back to the hydrothermal synthesis. For those of you synthesize nanomaterials, this technique much, it can scale up much easier, right? So we did that, then in literature, there are two precipitants have been used, ammonia and sodium hydroxide. So what we did is actually we used picked a different precipitant, which is we used the uranium, and also we used we used a mix of urea and ammonium nitrate. And then from the luminescence and also the decay time, we can see our samples are much better, show much better performance. So, this is, Okay, interesting. So the images look interesting now. But we got these nanoparticles, and especially when we use these two chemicals, okay, urea and ammonium nitrate, what we see is actually, we call this type of Coreshell nanoparticles. And we believe the core actually is very helpful to eliminate the surface defects. So that's why we see this better better persistent luminescence performance. So that's, oops, yeah. So maybe
Dr.
it's possible for me to run through the upcoming.
Yeah, why don't you just,
we'll stop here.
We'll invite our attendees. I know there's a number of questions, but we probably don't have enough time for those. We'll invite people if they can contact you by email with those questions. I think that would be good.
Sounds great.
Now, yes, if you could just very briefly take us through the upconversion slides, just the top level, a minute or two, and then everyone will have the slides to look at afterwards, and then we'll go to the summary. So thank you very much. Go ahead.
Sounds great. Sounds great. Yeah. So the upconversion process is, this is what we schematically we're trying to show here, right? So this is the conventional luminescence, and so is a Stokes shift, right? So that's what we talked before. For upconversion process, though, the activators, even they are at the excited state, they can continuously absorb extra energy. So then they can emit light at a higher energy. So this is the anti-Stokes process. So that's the basic, what it is. There's I'll skip that. That's just schematically. Why this is important? Because because of this, right? So we can get into this optical window for example, for the human skin. So that's what we are aiming for, and that's why it's important. So the first material we use is actually, for upconversion, right? The combination of ytterbium and erbium is a perfect, combination, and many people use these two together. But here, what we did differently is we use lithium co-dope this material, and we see that we get the phase transition, and then that actually helped us to increase the luminescence. And so for the green peak showing here, it increased by 14%. For the red emission, it increased by 18%. So because of the time, I don't want to explain to you why there is a peak, at that doping level. But that's what the basic idea. And then this is the other one. We get back to this spinel structure, and we still use this combination of ytterbium and erbium, but this time we doped it with the chromium. And so what we see here is, so when we're excited by UV light, our materials by UV light, we see this emission from the chromium. And then when we annealed our samples, to 700 degrees C, and then we see the upconversion, peaks are completely different. So, and once the samples are annealed at 700 degrees Celsius, we see this singular rate emission. So that's the important part. And then, yeah, I'll skip this. Oh, so Mike, you put back some of my old slides, right? Okay. So then, we were trying to why this happened, right? That's the one thing is, just by hydrothermal synthesis, we believe the dopants are mostly on the surface of the nanoparticles, and also they are not evenly distributed. But this calcination process, helps to get the dopants, inside of the nanoparticles, and also get evenly distributed. And so the energy transfer process, could happen between these dopants, and then eventually the singular rate emission will happen on the erbium. So that's what we proposed. So with that, what I want to summarize is, with these materials, I showed you the photoluminescence, radioluminescence, you know, the examples, and also I showed you an example related to persistent luminescence, and then the other one is the upper conversion process, you know, with these two materials. And so this one is drawn by one of my former students, and then recently we get these two the covers of two publications, and I would be able to design these two and also use a coronavirus model here. You know, this is one thing I think recently becomes important, and is probably, you know, we can explore some of these nanomaterials for how to deal with the coronavirus, and you know, I think that will be very wonderful if we can get to that. So with that, thank you very much for your attention, and I know it's been taking me too long. Yeah, any questions or comments? Really
Dr. Mao, thank you again for a fascinating presentation. From my point of view, it's Mike Wasecki. I just was not aware of all the different applications, biology and thermal sensing and all of those things of this class of materials. So thank you. Uskar, do you have a comment as we wrap up for today? Anything struck you on this presentation?
Oh. Yeah, I mean, it's been a great summary, the first part especially, and then the applications. All these like things, I worked on nanoparticles myself, metallic nanoparticles, but I wasn't aware of all these like doped scenarios with the metal oxides, right, and also the core and shell effects. Yeah, it's been fascinating. Thank you very much.
Dr. Thornton, Trevor, any comments, thing that struck you today?
Great talk, Dr. Ma. Thank you. I'm looking forward to seeing your progress and future applications of these ideas.
And that's my final question for you, Dr. Mao. What is the future of your own research group? What are you going to be looking at in the next 2 to 3 years?
Yeah, you know, that's a very good question, and also that's also one of the reasons, you know, I moved to Chicago. I think there's a very good advantage. You know, we are so close to organizational lab. For some of this, you know, some of the slides I presented, you know, I know we showed, you know, the improvement of the luminescence. But the next thing is I'm trying to talk about my current research group, and also some of my prospective postdocs is I really look like to take advantage of organizational lab to understand the structure and how the property correlation.
Excellent.
I think that will be more like application-oriented fundamental research. You know.
All right, very good.
So,
you know, let me mention now one more thing for our attendees. Dr. Mao, I'm going to click the button here, and a survey, the browser window will change. A brand new browser window comes up, and there's a brief 4-question survey. I hope our attendees will take just a moment and respond to that. Dr. Mao, don't respond to the survey yourself, or our moderators as well. And you'll still hear me while we're, you know, you'll still hear me talking while this window opens, and so there it goes now. So Dr. Mao, thank you again for the presentation today. I hope that I may have an opportunity to visit your lab sometime in Chicago. I'd like to do that, and I appreciate all the effort you made on the presentation today.
That would be great, yeah. It would be lovely, you know, inviting you.
Okay, good.
And also for those of you, you know, if you have extra questions, always, you know, please send me an email, you know, contact me. It'll be very nice to, you know, communicate.
Is it all right if I put your email in the chat window there so people will have it? Okay, yes, just please. 1 second, everyone. I'll put Dr. Mao's email right in the chat window, and then that'll end that part of the webinar today. Just a moment. Here it comes into the chat window. There we go. It's ymao17@iit.edu. So folks, thank you again. This officially ends the audio portion of our webinar. We'll leave the windows open for a couple of minutes so that you can complete the survey. Dr. Mao, thank you again. I'm going on to mute and turning off the recording.
Okay, thank you. Thank you everybody for attending my talk.